Okay, so center of mass and collision. And because I'm doing after my JEE advance, I mean, there is no point of me to like actually solve it for practice. So yeah, I'll be just explaining stuff, right? Okay, and that means that my speed might not be the best that it could have been because I'm not solving with that kind of approach. I'll just be explaining it. So anything that I know of, I will just explain how I do stuff, right? And I'm definitely not the best person to learn this from. Yeah, but let's do it. Somebody asked me to do it, and I'm gonna do it. All right. And also, actually, I said I would be doing it on Wednesday, but then yeah, I had some stuff going on Wednesday, so that's why it's now Thursday, and I'm doing it right now. Okay. So what do we have in syllabus? System of particles, center of mass, and its motion. Okay, impulse, elastic collisions. Right, so this part, elastic and elastic collisions, this is kind of new for me because I didn't actually pay all that attention for this part, right? Majorly just this is just the definition of center of mass and its usual properties. That's what I've been using till now. I didn't actually have all that much exposure to collisions, as in, you know, like the problems that you have with collisions, right? I didn't solve those many of them, and that's why I still feel like it's kind of a weak subject for me. Collisions, right? I know how to solve it. It's just that it's not as good as the other things with Newtonian mechanics. Anyway, let's start. Okay, so you got theory, then exercises, then last year ITG questions. Okay, center of mass CM of for system of particles, continuous bodies calculation. I know about that. All right, so was in center of mass? Just not about okay, whatever. Yeah, you don't actually need to read all that. I'm just gonna explain it first of all. So, what is the center of mass? So let's just do this for discrete particles first. So let's just say that you have point particles. So here's the important thing: we are saying point particles, which mean that they have like no length, no breadth, no size at all. They're just like on a point, and there's mass to them. And in some particular coordinate system, you are finding out what these guys' coordinates are. Like this guy will have x1, y1, z1 coordinate, and then it is mass m1, and then maybe this guy has like m2 mass, and then x2, y2, z2 as its coordinates. If there were like four coordinates, you would use those. If you're only limited to two coordinates, you don't need to have the third coordinate. You could just use x and y. But then in 3D space, you use three. Anyway, so you got this thing going on. Like you have two particles, three particles, n number, whatever amount of particles. Let's just say small n, right? So the last one will be like the nth mass, and then you just have xn, yn, zn as its coordinate, and yeah, just have a bunch of these, right? So what is the center of mass? Center of mass is like it's the position, so the coordinate defined by this thing. So it's like summation of how should I actually say this thing? Okay, this might look weird to you. Let's just call these guys like so this coordinate, yeah, this vector, if you want to, right? You can think of it like a position vector, right? So x1 I hat plus y1 j hat plus z1 k hat. So that's a position vector. So just call it like r1 vector. So this thing is our r1 vector, and then this summation is like mi vector, where I goes from 1 to n. So what that means is like you start off at 1, so you just have like m1 r1 vector, which basically means like m1 times x1 I hat plus y1 j hat and so on. So this is on the numerator, and then you have to divide that by the total mass, which is the summation of mi from I equal to 1 to n, right? So yeah, I mean, it's kind of like a weighted average if you want, which I mean, yeah, that's what it is. It's adding weights to our position vectors, and then you're taking the average, right? So if, for example, m2 was much higher than m1, then m2 would matter more. So let's say you have like two bodies, and one of them is like 4 times more massive than the first one, right? Then your center of mass will be somewhere over here, because yeah, I mean, like this distance will be, I don't know, I'll call this like, just say this distance is x, then this distance will be 4x. So for example, they gave you like the distance between them as d, then you could just say that okay, this point will be like 4 upon 5d away from this point, which has mass 1, this has mass 4, whatever. So you kind of do know these basic concepts in it, right? Because I mean, those are pretty common. Anyway, so that's the way center of mass is for discrete bodies. Now they also told you about continuous systems. So no need for you know getting the formulas and everything. Just have to apply this thing, but then extend it, right? So for example, I don't know, think about something. Okay, I'm gonna use a sphere, or let's just say a hemisphere or something. Maybe that's not the best thing to be using. I don't know what I should be using. Okay, let's use this thing. So yeah, let's just use this. So you have some random area. Okay, so this is a base area, and then you are making a kind of like pyramid thing out of it. So I don't know how many sides this has, even if it's not even a polygon in the first place. So yeah, it's just basically this thing stacked up, but then the area is decreasing, and the area is decreasing by x squared, but x is the distance from this point. All right. So yeah, like for some level, you could say you have this as our x coordinate. Then this thing, I'm still going to use this thing actually. So first of all, we should figure out what MIRI vector is. In this case, we only actually care about the x coordinate, right? I know. You'll be saying like, what about the y coordinate? What about the z coordinate? Because like this can be broken as x, y, z components. We'll just care about the x component first, and then we'll figure out about y coordinate, z coordinate. Actually, you won't figure out because most of the time they will have this radial symmetry, sorry, axial symmetry. So you won't have to figure it out. Just by symmetry, you could say let's say zero. Yeah, just zero because for one slice, it's okay. Actually, let me explain what a slice is. So what I'm doing is I'm slicing this solid into a bunch of slices with, let's just say, thickness dx. Let's just say it is dx because that's the increment in our x coordinate. All right, and so what's the area of this thing over it? Let's just see that our area is kx square, right? And in that case, like just say this complete thing is h. So this area, this call this as base area b. Our b will just be k times h square. All right. Okay, so for this thing your area is kx square, right, and our mass over here, that will be like the density of this thing times the volume of this element, which is just kx square, that times this thing which is dx by that thing, because it's like pretty much just like a cylinder, but then it has a bit of slant, but like ignore that. All right, this little volume, it can't do much. It is just approximately this thing. So then that's our volume, and that times the density is just the mass, right? So you got the mi figured out. What about the ri vector? We're just caring about the x coordinate anyway, and let's just say that this is our origin, so this is our o, right, and starts off right here, right? This is x equal to 0 point, and then we just have to multiply by x once again because ri, right? So it should be x plus y plus, yeah, you get the thing, x I hat, all that stuff, but just think about the I hat component, which is that times of x, okay? And you have to divide by, yeah, also you have to actually integrate that. So what do you mean by integration? It's just basically like summation, but in a more continuous fashion. So it's like the integration of this thing, so summation, integration, from I equal to 1. So I equal to 1, I don't know, yeah, like the complete body, just want to sum up all the elements, right? All the elements having this function thing, just want to sum up all of these guys. So we'll just start off at this point because it doesn't matter how you sum up, in the end you just have to sum up, right? That's the thing. So you can start off here, which is like x equal to 0, and you can move to this point like x equal to h or something, and then that divided by this summation. So once again, a summation is just an integration, and you're going from I equal to whatever. It's going to move from 0 to h, right? So x goes from 0 to h. What about the mi? So without this ri, your mi would just be this thing, right? I mean, yeah, that's the thing. So like rho kx square dx. So your center of mass for this particular continuous system would be just this thing, right? And it's the x coordinate of the center of mass, whatever. Some stuff cancels. Okay, you can just take these out because rho and k are constants, and then similarly you can take these out, so rho and k are constants, so just cancel these anyway. So you just got integration of x cube, which happens to be x power 4 upon 4, and it's going from 0 to h, remember that. Yeah, and then what about this guy, just x cube upon 3, it's going from 0 to h as well. This thing, it just becomes h power 4 upon 4, and then you divide by that, it's just like 3 upon h cube. It just becomes 3 4 h. Yeah, did I do that correctly? I mean, it should just be x squared over there. Yeah, well, the area is in fact just dependent on x square, right? Exactly. I mean, that's pretty obvious. As you move like this, this increases linearly, but then that means the area increases as a square, right? So your base could be anything, like square, it could be a circle, whatever. What it basically means is that the distance of our center of mass from this O point is just 3/4 h, which means the center of mass is like 1/4 h above the base. And since we proved this for any general base area or base shape, that means that you can like apply it everywhere. Like, so for example, you have, I don't know, a cone. So according to this thing, a cone should have its center of mass 1/4 h above it. And maybe they will also calculate this thing. We'll see what happens. Okay, so they are doing it for n discrete particles. Then whatever. Oh, okay. I think they did derive it somewhere, right? Okay, they did that for a hemisphere. Then for a cone, okay, 3/4 h. Yeah, so 3/4 h from this point. And now we just prove this for, wait, just wait a second. Okay, sorry for the interruption. Uh, yeah. So what we just proved is that this works for any kind of base area, and actually that's a nice thing, right? And in fact, there's a more general form of this thing, which basically says that if you have like n-dimensional pyramid, this sounds weird. Yeah, then you just have the distance from the base of our center of mass being like 1/n+1 h. Does that make sense? So for example, this is a three-dimensional pyramid, and then the distance from the base is 1/3+1 h. Yeah, so like for example, should I demonstrate with a circle or something? Okay, maybe I should not. I'm gonna do it anyway. So for example, if your system was this thing, so it's a triangle, or you can say it's triangular lamina. Yeah, and it has like uniform density and whatever. You can actually prove that it doesn't matter how this triangle is. Its center of mass is actually the centroid, right? For any triangle. Yeah, because like the distance from this line, the base, that should just be 1/3 now, because like it's a two-dimensional figure, so it's 1/2+1 3. So 1/3 h, the h is just this thing. So yeah, what point is there that is like 1/3 of this distance away? I mean, that's actually a bunch of points that satisfy that. But then you have the same thing going on for each base, if you want. And then what I get is like, okay, this is only going to give one single point, right? That's the only way it's going to work. And yeah, that means the centroid is the center of mass as well for this triangular sheet. Okay, so that's a nice thing to remember. Or you could just, do it, like actually calculate what it's going to be like, which I will not do. I'll leave as an exercise, because now you already know how to do it for continuous distribution. So then it's a piece of cake to do it for a triangle, right? What's the big deal? It's just 2D figure now, right? I mean, okay, so let's go to something more complicated. So let's go to I don't know, a hemisphere. So yeah, that's what they are doing. Hemisphere. Okay, so their method is this thing. Okay, using theta over there. I'm gonna use the same. So actually, let's explain what's going on. Actually, they are going to explain what's going on. So okay, so the figure shows a hollow hemisphere. No, we don't want hollow. We want solid. Oof. You know what? Instead of solid, I'll just say it's like a solid hemisphere, except, so subtract from that another smaller solid hemisphere, right? So that's a more general thing, and that you can actually apply that to this thing as well. We'll see. We'll see. So here's what I'm thinking of. You have this solid with an inner radius and outer radius. It's like hemispheres. Okay, and just want to figure out what is its center of mass. By axial symmetry, you can see that it's xy. Let's just say this thing is, or let's just say this is our x coordinate. Okay, from, what was I going to say? Oh yeah, from radial symmetry, you can say that our yz, in the yz plane, the center of mass must be, I mean, it's just this origin, right? Yeah, so when you project the center of mass on the yz plane, it should just become the origin. But what about the x coordinate? We know that the mass just lies above our yz plane, so there must be a positive x coordinate. But what is it going to be, right? Okay, so let's do it. Once again, you just have the mi. First of all, you'll have to figure that out. So what do we take as our element? I'm gonna take this slice of it if you yeah, okay, that will work. So okay, this is very complicated. So this is the slice of this figure. I'm not drawing it well, am I? Anyway, so right, what is the slice's volume? Okay, so first of all, you need the area. So you need this and this. And what is this, by the way? This is just, let's call this thing like theta, right? Call this angle as theta. Let's just say that the distance, like its radius is just capital R. Then this thing is R sine theta. And let's just say the inside radius is like small r. So this is R sine theta. Oh, it's not R sine theta. It's like just, huh, that's kind of weird. Okay, so yeah, that's kind of complicated. I didn't think this would be happening. Okay, for now, let's actually skip the more general case and let's do the not so general case first, because doing that actually gives you the more general case anyway. I will explain what's going on, but first of all, just do the less general case. So you have, oh god, that's not what I want to draw. I want to draw a circle. God, this AI is just okay. So here's our hemisphere. It's a solid hemisphere, by the way. So you have like it is in 3D. This is our capital R radius. Then as they are doing, it's gonna do the same thing. Actually, they're doing for hollow hemisphere for whatever. Just do it. So I'll call this angle as theta. Then what's yeah, what is this volume going to be? First of all, we need the area of this thing, right? Which will just be, you know, pi times this guy square, which is just r sine theta. It's like r squared sine square theta. Then next you need the h thing. So our h, if you want to call it that, this is just r cosine theta. This is the derivative of that thing. I should not say derivative. I should say the infinitesimal change in that thing. Differential. Yeah, that's the right word. So it's like d of r cosine theta, which is just negative r sine theta d theta, right? Yeah, exactly. So this is becomes like what, pi r power 3 sine cube theta d theta. I'm gonna skip the negative stuff. We can actually have that in there anyway, but we only care about the mass anyway, right? Okay, whatever. Just put the negative stuff. Who cares? So this is our mi. What about our ri? So we just care about the x coordinate, right? Which happens to be how much, like r cosine theta. So there you go. It's got r power 4 over there. Oh, it's not just mi. Actually, for mi, you also need a rho in the front because just a volume in the density make the mass. Then you got r power 4, and then it's like sine cube theta cosine theta d theta. That's a very integratable function. Nice. And then divide by, oh, just not yet. Actually, integrate this thing, and we'll go from theta is equal to 0 to pi upon 2. Now we have to like y pi upon 2. So at this point, this like was a 0 radius circle, and now it's like a big, the whole base itself. And it's, yeah, the theta is going from 0 to pi upon 2. That makes sense? Hopefully. And divide by the integration of mi thing, summation of mi, which is now just integration of dmi, if that makes sense. Right. So, you know, like the mass of this complete thing, is that a big deal to figure out? No, just 4/3 pi r cubed times the density. There you go. Easy as that. We already figured that out. Oh, it's not 4/3, actually 2/3, sorry. Hemisphere. Yeah. Okay, that explains it. So this cancels and this cancels, and also like r is a constant, so actually just got r over it. And what does it become? Negative 3 upon 2 integration 0 to pi upon 2. You just have s cube c, which means s cube like sine cube theta, and then d theta, right? So this little shorthand, I will be using this a lot anyway in all of my videos. So yeah, and then c d theta, that is actually ds. I know it sounds weird, but then just deal with it. S cube d sine theta, the differential in sine theta, and it's going from 0 to 1. Yeah. So what's this going to be? Just negative 3 upon 2, and then you got 1 upon 4, and then just this thing. Did I mess up somewhere? Probably not. So it's a uniform hemisphere. Okay, we just want a complete solid hemisphere. So they are doing it like that. So why is mistake? Yeah, there's no pi involved. There was a pi involved in the hollow hemisphere thing, right? Yeah. Here there's no pi involved. Where'd that go? Just 3 upon 8 r. Okay, whatever. And yeah, that's what it's. Oh, so there's like a capital R missing because that got didn't get actually cancelled, and we have to write that over there. Okay, so this is the thing. It's just negative 3 upon 8. Oh, and this actually negative also cancels, right? But this should also be in negative. You know, the differential stuff. Anyway, so that cancels. Yeah, nice. Correctly, most likely I did. Yes. That should not have been that negative, right? Because we know it's actually above it, right? Yes, we're going for a theta equal to 0 to this guy. Oh yes, like if I actually did the dm thing correctly, that those negatives would cancel anyway, and then just get like 4 or 5. Yeah, so that negative should have cancelled anyway. Yeah, I just don't think what it too much. Sometimes there will be small changes that makes like the signs change, but not a big deal. So you don't need that negative actually, just 3/8 of r, right? Which is exactly what they got. So the y center of mass, which is in this case the x center of mass, whatever, that's just 3/8 of r. So it's 3/8 r above the center, right? And it's the center of mass. That makes sense? Okay. So yeah, that's awesome and all. But then we also want like a general case of this thing. So you might ask me like, what's the general case? What do I mean by that? The thing that I was doing before this. So you have a hemisphere, but then you take out another hemisphere out of it. So now you might be thinking, okay, this is already complicated. How do you do this? Well, you can use the fact that you already know the center of mass of a hemisphere, and taking out a hemisphere is like adding negative mass. Sounds weird? It should, because this is something that only makes sense when you're talking about electrostatics, right? So adding negative charge, adding positive charge, but then negative mass weird. But you can use this because like a calculation trick. So add negative mass to it. Now this guy's center of mass was at 3r upon 8, right? And this guy's actual mass was just what? This times of 2/3 pi r cubed. You know what? I'm just gonna skip those 2/3 factors because it doesn't actually matter, right? Yeah, because like it's gonna get cancelled anyway. Uh, right. And yeah, actually, you just have two different bodies, and then you already know the center of masses. You can treat those center of masses as point masses to get the center of mass of the final combined body, right? Because the summation stuff, it works out exactly as you think it will, right? Yeah, I mean, what is it really? Just summation of, so the actual center of mass is just summation of mi. How do I even explain this? And this summation contains the mass elements like mi, ri vector, and it's like combined body. Okay, combined, and then upon summation of mi combined. But you can split this as summation of mi, ri body 1 plus summation of mi, ri body 2, and upon summation of mi plus summation of mi. What am I doing? Body 1, body 2. And if you remember, well, this thing can be done as summation of mi, it's like mass of the body 1, that times of the center of mass, the coordinates of the center of mass, right? Which means you can actually treat the center of mass as point particles to get the final center of mass, right? No big deal. Okay, so you got this thing done. So what do you have? I mean, those 2/3 pi r cubes, 2/3 pi is gonna cancel anyway. Just have r cubed. So this is the thing, and minus 3 upon 8. Call this radius a small r. So just have small r times r cubed. Right? Center of mass coordinates the mass or something proportional to it, and then divide by that. Divide by the total mass, which happens to be how much? Oh, also you need like density and all that stuff. Yeah. Uh, that's gonna be kind of complicated. Oh, we don't actually need that because we just need a position of the center of mass, right? And if it's like uniform density, it's gonna work out anyway. Okay, so what do you have? Just the total mass, which, yeah, once again the same thing, like r cubed, but now you don't have that 3 upon 8 r factor, and then minus this thing, which is like what, 3 upon 8 delta r power 4 upon delta r power 3, right? That makes sense. This delta basically means like just a change. So you're going from this radius to that radius now, right? And you could extend this kind of to actually get the center of mass of, you know, a thin Thin solid hemisphere. Okay, a hollow hemisphere, right? Exactly. And we actually have what, pi and stuff over there. It's kind of a weird thing going on, isn't it? Like, this would just give us like 4/3 over there. Wait, did I mess up somewhere? Just got the mass. And that's the mass also. The position. Which is negative over there, but well, yeah, this should actually work. This should work. Huh, the differential method is for some reason not working. This is the center of mass of this combined thing, right? Exactly. So then when you make these guys approach each other, like this approaches that, then just we are taking the derivative or something like that. Well, this should actually work out. But for some reason, like seeing half r as our value, which does not actually make any sense. How can that be the thing? Wait, something's not right. The mass change, right? Like 2/3 pi r cubed. Of course, of course, of course, of course. Wait, something's not right about this. How could this be just the derivative, right? Yeah. So, okay. Uniform semicircular. Oh, it's a different thing. Sorry. Oh, okay. This was completely different. And no, not a hollow hemisphere, but that go. Not a semicircular. Okay, where is it? Didn't they actually do a hollow hemisphere as well? Uniform semicircular ring. Nope. Uniform semicircular disc. No. No. Yeah, hollow hemisphere. So it's r upon 2, and as you can see, this actually works because the delta r power 4, as it reaches a limiting case, you can actually write it as like dr power 4, if that makes sense. And dr power 4 is just like 4r cubed dr, and then this thing is just 3r squared dr by the same logic, and then that is of 3 upon 8, of course. And yeah, this cancels, this cancels. When I say cancels, you mean like, okay, I don't need to explain that. This is physics, so it's okay to just cancel it. Okay, this cancels and then just get 1 upon 2. So 1 upon 2r, right? Yeah, that will be the center of mass's location, or the y coordinate, or the height coordinate of the center of mass for a hollow hemisphere. And yeah, that's awesome. So what did we get? Basically, that this is the formula that we'll be using for both of these situations. And then also actually I made a formula for these two cases as well, actually multiples of these cases where you have any variable angle theta. What was this like? It was like r sine theta upon theta, if I believe that. Oh, theta was the half angle actually, not the complete angle, right? So for example, center of uniform semicircular ring. Okay, right. So for this case, we use this thing, and so over here, what you have is that the theta is, oh, it's not just this. Actually, you have e power I theta, right? So this mass's location, where that, what do I actually mean by this value? So you have a part of ring, an arc, and the center of mass will of course be on the angle bisector line, right, of these two radial vectors. But what's the distance from this point? Well, that distance is actually this thing. It's just r sine theta upon theta. And right, let's actually see if this works or not. So first you have position center of mass of a uniform semicircular ring. So you just have, and theta is measured with this angle. So over here theta will just be pi upon 2, and then just have r times 1 upon pi. It's like 2 upon pi r. So it's 2 upon pi r from here, right? And it's actually like this. The angle bisector is this, and it's 2 upon pi r. Okay, let's see what did they get. So yeah, 2 upon pi r, exactly the way we predicted. And it's like a more general version of this thing where you have this. So this is like, yeah, I mean the same as this thing, almost, right? So you have two different radii, and this complete thing is of uniform density, and then this angle, as always, like this half angle is theta, and center of mass is somewhere along this line, but where exactly? What's the distance from this point? That is given by, I think it was this thing, 2/3. It's like r squared, right? Yeah, exactly. So 2/3 sine theta upon theta, and then you just have delta r cube upon delta r square. So as you can see, this works for the differential case where these two radii approach each other. Just becomes like 3r squared dr. This becomes 2r squared dr, that cancels with this thing, and we just get like r, just r, and that's like sine theta upon theta times r. That's the one that we saw before. And it's not so complicated to prove these two formulae if you know about complex numbers and things like that, or even if you know a bit of trigonometry, right? You can easily derive these things. Yeah, so this formula works for, I mean, any general case of this form. So yeah, let's see. Find center of mass of a uniform semicircular disk. Right. So in this case, our delta r power 3 is like just r power 3, and this thing is just r squared. So like you just get r basically, right? Because small r is 0. So you just get 2/3 sine theta upon theta small r, and that's along the angle bisector and all that stuff. And just have 4 upon 3, huh? That was kind of interesting. Oh, okay, there's like pi involved. Okay, so 2/3 sine theta is 1 and theta is pi upon. Okay, that's fine. So just 4/3 pi times r, right? So as you can see, this method works, and it works for even more cases than what they are giving us. So you don't have to derive this all the time. Just remember these formulae. I mean, this formula and with that go, this formula. Those are only the two formula that you need for these cases. And then there are a lot of other formula that you will need. But for now, just need to know these two things and some common logic as well. So find position of center of mass of uniform solid cone. We already got that one, right? It's 3/4 h from this point. You know the thing. Okay. Okay. What is this thing? It's uniformly rod of length L, cross section area as well as density varies. Right. So this thing you can just do it by, you know, the usual derivation. No need to make a formula for this case, right? Whatever. Oh, and by the way, we don't actually think what happens if theta approaches 0. First of all, it should be a special case, right? So our special case is that our small r is 0. So then just becomes like sine theta upon theta and that times of r, and then we got 2/3. Okay. So that's right. That's our case when it's not actually, yeah, it's like this complete region is of uniform density and it's planar region, whatever. My question is, as theta approaches 0, what do you think this thing represents? Think about it. What does this really represent as theta approaches 0? The mass of any ring, yeah, that thing is actually proportional to any ring of a particular thickness. That a small ring actually, that is proportional to, you know, this distance squared, right? So this actually represents, this is, no, okay, sorry, this distance linear, right? Okay, so this is just proportional to this distance, the mass of this company. It was like 2 pi r theta r times dr times rho. You get the thing, right? So what this actually represents, as we get theta to 0, as we approach 0, what happens is like this actually represents a stick with varying linear density. Actually, the linear density varies as a linear function of this distance x. That's what it represents. Nice, right? Yeah. Uh, and in that case, like this thing approaches 1, so just get 2/3 r. So what that means is like if you have linearly varying x, linearly varying linear density, well, that's kind of weird. Our center of mass will be at 2/3 r from this point, which makes sense. I mean, it has to be bigger than half r because we have more mass over here, and it's 2/3 r. That's what we get. And you can also try doing it the usual way, and it will still work out. Yeah, just blind faith in this formula because I already derived these. Actually, made a, you know, kind of compilation of these kind of formulae. Yeah. So okay, we don't want that. Just wait a second. Okay, so you got these two formulae, right? We'll be using these. Come on. I mean, like we will remember that anyway, so no need, right? What was that one? Wait a second. 3/8. Right. I think we should actually probably remember this thing. So you got 3/, actually more right now. So you have hemisphere. Just gonna write it. Hemisphere. Hemisphere. The center of mass is 3/8 delta r power 4 upon delta r cubed. And then you have What do you even call it? Like a disk or like arc? Arc will be good. That's just what 2/3 sine theta upon theta, and then you just have, where'd that go? Delta r cubed upon delta r squared. Awesome. So yeah, I'm writing this down because most probably we'll be using these later on. Anyway, let's just start now. Start with the exercise, that is. So in chapter exercise 1, right? Okay. So okay, 3-point passes, vertices of equal triangle, side 1 meter. If x center of mass, y center of mass are the coordinates of their center of mass. Okay, then the value of x center of mass, y center upon y center of mass is. Come on, are you serious? Just have to. Okay, whatever. This might. Okay, this might be actually weird. Side 1 meter, but you can use complex numbers to represent these things. Now this might be very weird for some people. Uh oh, I think we should stop. We should stop.